Hey, what do you know? It's time for another exam. You learned a lot in this chapter, right? You learned a lot about sequences in the series, and it really seems out of place, but I promise you, we're gonna make use of it in chapter 6. Okay, so we're gonna go ahead and start off, all right, by reviewing some very basic things about sequences, and in particular, we're just really gonna be talking about convergence versus divergence, okay? So we just have a bunch of sequences here, and we're gonna determine if they're convergent or not. Okay, and really a lot of these just come down to, do you know how to find limits? So we're going to blaze through these very, very quickly. Let's take a look at this first one here. We have a sequence an. It's defined by the rule n over 2n plus 5. Remember that sequences are just functions on the natural numbers, so, well, on the non-negative integers if you want, okay? 0, 1, 2, 3, and so on. You plug those in, you get new numbers. All right, so we want to figure out what this limit is. Again, this is just a basic calculus 1 limit. Okay, so we're going to go ahead and look at this limit here. Okay, some of you are already shouting at home probably already know the answer. Okay, but for those of you that need a refresher here, take a look here. N over 2n plus 5, okay? I got linear over linear. It's equal heavy, as I would say. So we're going to go ahead and divide out the highest power in both parts. Okay, the highest power that it appears across the overall fraction is n to the first power, so I'll divide top and bottom by n. So what I'll do here is I'll do the following. Okay, we're going to multiply top and bottom by 1 over n. Okay, n times 1 over n gives me a 1. And then on the bottom here, I'll get 2n times 1 over n, that's a 2, plus, then multiply the next term, 5 over n. And of course, as n goes to infinity, 5 over n goes to 0. So what's left over is 1/2. So we say that this sequence is convergent. Now, a point of order here, remember that a convergent sequence doesn't always mean you have a convergent associated series, okay? I encourage you to look back at the divergence test, the nth term test, okay? Little exercise for you at home. If I were to sum all the corresponding terms of the sequence, is that series convergent? Spoiler alert, no. All right, let's go ahead and look back. Let's look at the next one here. We got another one here. 5 minus 0.09 to the n, something that is geometric in nature. Okay, let's go ahead and write down a little fact here, okay? I'm going to use the fact here that r to the n, any sequence of this type, if my eraser will work, there we go, any sequence of the type r to the n will go to 0 if the absolute value of r is less than 1. Okay, remember when we talked about geometric series, right? That was our notion of convergence of the geometric series. That's the same thing for the notion of convergence for a geometric sequence as well. And we can see that if we write this in a particular way. If I instead write this as 5 minus, instead of 0.9 to the n, let's write this as maybe, say, 9/10 to the n. Well, that's certainly a fraction smaller than 1 in absolute value. Okay, think about it. If you put in 9 over 10 times 9 over 10 in your calculator and you just keep hitting enter, those numbers will get small, well, soon pretty quickly. Okay, but because that term goes to 0, okay, we have the leftover here bit 5. So this is indeed a convergent sequence. Now ask yourself, is the corresponding series convergent? No. All right. New one here, 2n plus 5. This one should be a no-brainer. Okay, we know here, we're just going to take the limit here. This is a super easy one. 2n plus 5. Okay, and if you notice, that was the denominator of the other fraction up there. Hey, take a look at that, right? Well, 2n plus 5, right, that's just a linear function. It's just going to keep getting bigger and bigger and bigger. This is a divergent sequence. All right, the next one's going to be one of our interesting ones here. N over log n. All right, we're going to look at n over log n. Now, remember from Calculus 1, we have L'Hopital's rule, okay? If you get one of these indeterminate forms, something like 0 over 0, infinity over infinity, or even some of the funkier ones like 1 to the infinity, infinity to the infinity, 0 to the 0, that's when you use L'Hopital's rule, okay? And in particular, when you have it as a 0 over 0 or infinity over infinity, as you do in this case, you take the derivative of top and bottom separately. Okay, so what we're going to do is use L'Hopital's rule here. Okay. We use L'Hopital's rule here. I encourage you to review that from your Calculus 1 knowledge. Okay, we're going to go ahead and take the limit here as n goes to infinity. We're going to take the derivative of top and bottom separately. Okay, the derivative of the top here, derivative of n, is just 1 with respect to n. then the derivative of log n, that's 1 over n. Do a bit of fraction magic here. Okay, keep, change, flip. We all know that's the action. So 1 over n gives us just n. And, well, of course, if I just keep putting in bigger and bigger numbers, I'm just going to get bigger and bigger numbers. So that limit is infinity, and hence this is a divergent sequence. Okay, now also consider its reciprocal, okay? Log n over n, okay? Very similar in nature, except that one's going to be convergent, okay? Again, by L'Hopital's rule. Sine of n, okay? This one's going to be very tricky, okay? Well, not so much. We have to consider sine of n. This is a discrete sequence now. So I want you to think about it like this. Let's go ahead and draw a little picture off to the side here. Okay, sine of 0 is 0. And if I were to just sample this at certain points here, well, it goes up and down, up and down. It's not a very good picture, but that's fine. But it just keeps going up and down, right? Does it settle on any one number? No, it doesn't. It oscillates, okay? That wave just keeps oscillating up and down, okay? Just an undamped, simple harmonic motion, no friction, okay? Some nice physical principles there. So this limit does not exist, okay? And because the limit does not exist, this is divergent. Okay, so remember, sine of n, okay, and consequently cosine of n, okay, your nice trig functions, if they're just by themselves, okay, those oscillate and those limits do not exist. And if the limit does not exist, we say that the limit is divergent. Remember that in order for the limit to exist, it must settle on a single number, okay? Now let's take a look at this one. This one's a really fun one, cosine of n over n, okay? There is a lot of ways you can work with this one, and honestly, one of my favorite ways is to use the squeeze theorem. Okay, so I'm going to go ahead and squeeze, but I'm going to squeeze in a slightly more powerful way by using absolute values. Okay, so we're going to go ahead and use one of our basic facts here. I'll just put it here in the margin, is that the magnitude of cosine x is always less than or equal to 1 for each x. Okay, the graphs of sine and cosine are bounded above and below by 1 and minus 1. So in magnitude, sine and cosine are less than or equal to 1. Well, okay, how does that help us? Okay, so we're going to go ahead and look at the absolute value of this sequence an, which is cosine of n over n, an absolute value. And now I'm going to go ahead and use a property of absolute value here. It's multiplicative. Okay, and we're going to also note here that n is bigger than or equal to 1. Okay, so the absolute value of a positive number is just the number itself. So we'll have cosine of n, an absolute value on top, and I have an n left over on the bottom. Now we're going to use our fact here because cosine of x is less than 1 in absolute value for each x. I can replace the numerator by making it less than or equal to 1, and then I have 1 over n here. So our unknown thing in absolute value is less than or equal to 1 over n. Now we have a nice powerful result here, okay? We know that our unknown sequence, okay, an, is bounded from below by 0, okay, because absolute value is always greater than or equal to 0. But we also know that it is less than or equal to 1 over n. Now, remember what the squeeze theorem says, right? You have something in the middle, and you know that the two things on the end, okay, the things that sandwich between them, okay, that's why it's also called the sandwich theorem, okay? If the two things on the ends go to the same limit, the thing in the middle is trapped. It's got nowhere to go, and so you're basically in a mating position. Okay, it's trapped, nowhere to go, no more legal moves. So the only place that the middle thing can go is the thing that the other two has gone to. So note here that in limit, as n goes to infinity, 1 over n goes to 0. Okay, and then of course 0 is a constant. So as a consequence, an must go to 0. Okay, so by squeezing, or if you want, by sandwiching, okay, an goes to 0. So this sequence is convergent. Okay, very powerful result here. Okay, this awesome squeeze theorem. Okay, you can even use this for some comparison tests, but I'm going to leave you guys with a bonus question here. Can you actually use a comparison test here to determine if the corresponding sum converges or not for this one? We did something like this in one of the previous videos. So now we looked at some of the basic things for just looking at sequences, okay? Just really, it's just limit exercise, all it is. Okay, we haven't really done much of anything new. What you really need to keep in your pockets, okay? Not literally though, but what you really need to keep in the pocket is just L'Hopital's rule, when to use it, how to use it, and some of those basic limit rules from Calculus 1. All right? So we're going to go ahead and keep going, and the next video is going to be an application of some of the basic sequence theorems called the monotone convergence theorem. And I'll see you in the next one.